on Tuesday, and definitely yes, you can use whatever symbols you want as long as my marker can understand your work. That's all that matters to me, and that you show your work and don't skip lots of steps. And the other question is, why is physics so hard? So it's very important to me that you learn physics and that you are prepared to, there's some very, very brilliant people, much smarter than me in this room, who may go on to take second-year physics and do PhDs in physics and be the next generation of researchers to go and invent quantum computers and win Nobel Prizes and solve climate change and all these things. Like physics is a research field, and this stuff may seem maybe a little abstract at times, but it is these are the foundations for going on to the next year, and I'm trying to get you prepared for that in case you ever might want to do that. And I think that some of it's kind of useful just for understanding your life, like bowling and swinging around your backpack. So actually I wanted to start with a couple of, I need some volunteers for this next one. So I need one for the first one. I need someone who can roll a bowling ball. Do you want to, can you roll this? So the problem here is that there's no holes in this bowling ball, but you gotta, if you stand over there, it's heavy, and I want you to roll it towards me, and I'm gonna try to turn it using this rubber mallet. So put this down. You gotta really just, right towards that expensive looking speaker. How's that? And then I'll try to turn it. Okay. So I'm hitting it towards sort of the center of circular motion, and it's going around in a circle. Okay, thank you very much. Thanks for that, volunteer. And for the second experiment, I need somebody who has a really heavy backpack. Andy, do you have a heavy backpack? Perfect. Then you need to come up here and kind of hold it. So mine is already empty. I should but kind of hold it and twirl it around in a circle, and I'm going to watch. There you go. So you can see the sort of diagonal force there that she's pulling inward. What is your name? Nora? So Nora's pulling inwards. Okay, fantastic. Thank you so much. Great. So now you're on video. Okay, so we're going to analyze those two experiments now, if we can. That's called Observational Experiment 5.1 and Observational Experiment 2, I guess, 5.1. And by the way, on the first few slides today, there's going to be the little addendum that Chapter 5 material will not be on Tuesday's Test 1, but it will be on Tuesday, November 15th, Test 2, and it will be on your final exam, of course. So you can kind of relax a little. But, okay, so this was me hitting the bowling ball towards the center of circular motion. I was trying to turn it so it didn't hit that speaker. And as I was turning it, it ended up kind of going around in a circular path. And the way that to get it going is I had to tap it directly towards the center of the desired circle. So to analyze that, I would say there's three objects interacting with the bowling ball. The earth, which is the gravity force, the floor, which is the normal force, and we assume that the force exerted by the floor is perpendicular to the floor's surface. That's another way of saying we're neglecting friction. Although I think that on this carpet, there is a decent amount of friction, yeah, because it slows down and stops. So it'd be better to do this on a hardwood floor or something. The force diagrams, and then with Chapter 5 problems, you're often kind of having to look at things in 3 dimensions. And the way you do that, I can only draw in 2 dimensions. So sometimes I'll draw 2 force diagrams, one from like a side view, and one from a top view. Or I think here I draw the sketch and translate part from top view. Sketch and translate, you look is top view to see what's going on. And then the force diagram, I do the side view. Diagram is the side view. Because two of those forces from looking from above would be right directly towards you and away from you, and it would get a little complicated. So, and it's sort of weird. You do a top view here, or sorry, side view from here, or side view from here. In both cases, I am tapping on the ball with the mallet in a direction, a sideways direction, that's towards the center of circular motion. Okay. All right. And then Norba's doing this swinging around her backpack, holding the bag by the handle, and you might have noticed this sort of diagonal thing there, diagonal tension line between the backpack and her arm. Your arms pull the bag at an angle with respect to the horizontal. And so I think there's only two forces on the bag in this case. It's not touching anything except you're just holding on to it. There's kind of like maybe a tension force. Maybe one way of looking at it. And then gravity. Mass of the bag times g acting downwards. And so the way I might analyze that is I might define r is towards the center of the circle, y is up. And so we have sort of f sub r and f sub y and some angle theta. So we know that the sum of the forces in the y direction equals 0 since the bag travels in a horizontal circle. It's not accelerating up or down as she's twirling it around. It's so f sub y is 0. A sub y is 0. So that means the sum of forces in the y direction is going to be probably, well, it's going to be f sub y up minus mbg is equal to 0. And then the net force is in the r direction, which is called the radial direction. And it's a little hard to see what it's pointing at on the side view, but it is pointing towards the center of the circular motion, the center of that horizontal circle that your bag is swinging at. Okay, so my idea was here that if this bowling ball had not been hit, it would have continued at a constant velocity in a straight line until it hit that speaker over there. So my, I guess, hypothesis is that when an object is moving in a circle, the sum of all the forces on it, exerted on it, is directed towards the center of the circle. And if you remove inward forces, the object should cease to be on a circular path. It should instantly start going in a straight line. Should we aux plate? Pius has set up a demonstration here on this table, so you can see it. It is a horizontal table in which it's been fairly leveled here. You can roll things around on the surface. And in particular, you can roll it in this track to go around this way, I guess, which way's which? This is clockwise, counterclockwise. I am going to roll it, let's start from here and roll it counterclockwise and see what happens when the force goes away. Okay. Oh. I totally forgot to do something. Do you remember what we were going to do? It's because I got my slides in the backwards order. There's a learning catalytics, couple learning catalytics questions today and a survey. Let me give you a minute to discuss this. And I don't know how this is going to work. I made this into a region thing. So I want you to kind of tap your finger where you think A, B, C, D, or E that it's going to go. Sorry. Going back and forth. That's the question you should see in your learning catalytics, I hope. And how's it look? just took some time. Okay. Hopefully you can see this diagram and tap on it. And the trick is here to remember, you're looking top view down. So gravity would be like into the page in this. And it's a Probably should have done this before the demo, but okay. It's a great bowling ball. Okay, let's take a look at what I've got on my screen here. I'll show you the answer. If I go, let's see here. Laptop 2, send to all. So you can kind of see where people have been clicking. I think it just goes along C. And I can see that sort of D or E are pretty popular answers there. I got 77% in the region I like. Let's go back to aux plate for a second and see if we can convince ourselves that I'm right. Seems to just as soon as so if you drop a tangent to the circle right there, you put the ruler there just to kind of guide the eye. Whoop. Ooh. If anything, I've got the tangent a little wrong. Okay, as soon as that inward force goes away, this ball just wants to roll in a straight line. And it's sort of similar for any circular motion. And this is the trick, is that circular motion or any turning motion actually requires acceleration, even at a constant speed. So in physics, we use acceleration in the vector sense to mean the change in the velocity vector per time. So you can imagine a vector, like if you're driving north or something at 100 miles an hour, and you turn to go east at 100 miles an hour, you haven't sped up and you haven't slowed down, but you've definitely changed your direction. We call that in physics an acceleration, and you can measure it in meters per second squared. And we're going to get more into that next class. What time is it here? Yeah. How are we doing here for time? We're doing all right. I'm going to do a couple more chapter 5 things, and then I'm going to go back and do some chapter 4 stuff to kind of talk more about what's happening. I've got one more. So C is what I like. Tangential, thank you. So glad that you're here, Pius. Otherwise, students would be yelling at me soon. So, the tangential velocity at the moment it suddenly is no longer accelerating because there's no net force towards inward. It's just going to obey Newton's first law after that. Constant velocity in a straight line. So, and then this idea of why do we study circular motion? Well, every curve has a radius. So here is a Google Earth view of the intersection of Highway 427 and the 401, and it's got all these ramps. Well, any region of any part of this curve, you can actually get a radius. And so we have this R, like if you're on one of these tight little circles, the radius of this circle is only 75 meters. If you're on a more smoothly turning part of the highway, like this little part right here, you can kind of fit a dashed line that matches, like a circle, that matches the curvature at that point. So you would say that at this point, the radius of curvature is now 410. So a more gently turning road has a larger radius of curvature. So if you fit it to a circle, that circle has a larger radius, or even, imagine really large, right here, this sort of region here, it's 730 meters, almost a kilometer in radius. And I think it turns out that the acceleration, remember I told you there's an acceleration value? I think it turns out to be something like v squared over r. This is the radial acceleration, that's a squared. So if you speed up, you need more acceleration. And if the radius increases, you need less acceleration because it's on the denominator there. But we'll get more into that when we come back on Wednesday. Let's do one more learning catalytics and talk about this. Give you a minute to think about this one. So I got a top view, and I've drawn a side view in the sketch. What is the name of the force that keeps the car on the curved path? I need an external force on the car, right? If you know it, just tell your neighbor and click it in, please. Okay, yeah, this wasn't very fair. One thing I did here is I put on something called rolling friction. Let's just forget about that. I will just say there are some textbooks that deal with this, but this is going to be not a subject, it's not it anyways, of Physics 131. So that's not what I was looking for. And it also happens to be wrong. So, but it's one of the other four. So maybe if you did answer rolling friction, maybe try to choose another one, and then in 10 seconds. Okay. Going once, going twice, and stop. So out of curiosity, 67%, so it's this static friction once again. Okay. So let me just discuss this a little bit. So first of all, gravity and normal can't be it, because these are both not in the direction, not toward the center of the horizontal circle. So what you have to imagine anytime you're turning is that if you kind of fit your path to a circle, where would the center of that circle be? So if you're turning left, the center of that circle is somewhere to your left, I think. And so that's what's going on here. It's a horizontal direction. So we do need friction, because friction is the horizontal force there. And so what's rolling friction? So rolling friction is actually that thing that slows down this bowling ball. It's rolling without slipping, but we know that its energy, its kinetic energy kind of goes away after a while, so there must have been some heat that's generated in the carpet, probably, and that's what slows it down. And that's something that some textbooks call rolling friction. But it's not really, it's kind of a confusing friction to talk about, so I'm not going to do that, because it's combined with one other thing, which is static friction. So kinetic friction, by the way, it's a sliding friction which always acts opposite the velocity of the object. So if the car is traveling like north in this view, top view, then the kinetic friction is south. And that's also not in the direction towards the center of the circle. It has to accelerate west, right? So, and remember, kinetic friction only comes in if you slam on the brakes and lock all four of your wheels and go screech along. then that's kinetic friction, and you're not going to stay in the circular path. You're going to go straight off into the ditch, but slowing down. Okay. So it's rolling without slipping, and it's called static friction. Okay, let's do a couple more slides to just get you started on this stuff, and then I'll talk about the test more. So an object's acceleration can be decomposed into components that are parallel and perpendicular to the velocity. So if I look at an object which is starts here and kind of goes like this. So this is the path. It goes this way and off that way. And I look at, for example, right here or something, then I think the textbook usually uses green to denote velocity. That's the velocity vector. And this is going to be tangent to the curved path. Okay. And then the textbook also uses this orange usually to denote acceleration. And maybe if it's speeding up or something, I can put acceleration like that, A. So what we can do is we can set the t-axis to be in the direction of v. So I'm going to define my axes like this. So, and then a perpendicular one. So the t-axis and what's called the r-axis. And they are at right angles to each other. So instead of doing x and y, for some reason I'm doing t and r, but they just mean directions. And I'll tell you what it means in a second. What is r? So then what you have is now you can decompose that a vector into two components. So maybe if we go back to orange or something, and we have a, which looks like this. There's a, the hypotenuse. Then there's two components. There's the radial component and the tangential component. A sub t and a sub r. So that a t squared plus a r squared is equal to the actual acceleration, right? And they mean two different things. So the real acceleration is on some diagonal. The component of the acceleration that's tangential to the velocity is what speeds it up or slows it down, changes the speed. And the component of the acceleration that's perpendicular to the velocity only turns it, but without changing the speed. And that's how we do it. But they're all measured in meters per second squared. And this is why an object that's changing direction always has an acceleration. Well, in the r direction, I guess. In the r direction. Even if it's not speeding up or slowing down. So we have something called uniform circular motion, which is the speed is constant. No matter which dot is selected, if you find delta v, you have to do these little arrows. As it turns, delta v is always going to be towards the center of the circular motion. So speed is constant. So a has a zero tangential component. Okay, so it's not speeding up or slowing down. But there are delta v's, or slowing down. I think that's pretty much it. So, okay. I think we'll continue this. Let's continue on Wednesday, October 13th. We're going to come back, and we'll be back, sort of continue where we left off. What time is it? Yeah, I got some time. I wanted to talk more about the test and maybe do one more example from chapter 4. It's good stuff to know in the test. So, okay. So yeah, back to chapters 1 through 4. We've got a term test coming up the day after Canadian Thanksgiving. We're going to all meet in the EX building. at 6 o'clock on a Tuesday, so hopefully you can be there. There's going to be 10 multiple choice questions for which you bubble in an answer on your answer sheet. And then there's going to be one written answer question, which you sort of write on the blank other side of your bubble sheet. And then those both get scanned in, and there's a human marker who is going to be going through and marking the written answer question and making sure that you showed your work, and that maybe even if you got the wrong answer, you get some partial credit for doing the right steps and stuff. So there's different rooms within the EX building. EX 100 is you kind of go in and go down the stairs. EX 200 is just up the stairs. And then there's some more stairs which take you up to the 3rd floor for the 3 rooms that are up on the 3rd floor, but a little smaller. And we have the whole building booked. So every room will be filled with PHY131 TAs, some of whom you may recognize, who'll be wandering around and helping you get started. Okay. And if you're in the alternate sitting or something, go to the room that you were asked to go to. Okay. What else? So at these things, what we do is after the test gets going and you're doing it, then quietly what will happen is these invigilators will be walking around from desk to desk and asking you to sign on the signature sheet. And so they have a signature sheet with your name on it. You'll find your name and sign your name beside your name. And then at that same time, they'll look to make sure you have the right things on your table and that you have some photo ID, like your T card, and they'll kind of look at your eyes and look at your photo ID and make sure you kind of look like who you're supposed to be. Allowed aids include a calculator, which I thought I had on here. There it is. An aid sheet, don't forget that, which you can write anything you want on both sides of a letter-sized piece of paper. You're also allowed an English translation dictionary that has to be paper. It cannot be electronic. You're not allowed anything that's electronic other than your calculator. Okay. But if you wanted to know the definition of the word raucous in Mandarin, for example, you never know. And I also, if you go on the Course Quirkus site, there's a module underneath the practicals module called Term Test 1 Information, I think. And I've started posting some little tidbits there, like what exactly does the first page look like, so you can read the instructions ahead of time. Or anyway, that's about it. What does the bubble sheet look like? Eventually, that's where I'm going to be posting the solutions to this term test, so you can check that out. Okay, stretching. Okay. Yeah, you're not allowed to look at your phone, so you got to kind of put that away. Also, if you have a smartwatch, Apple Watch or something like that, you have to take those off. It's another one of the things that all the invigilators are going to be looking for. You can't have those objects in your pockets either. They have to be kind of off your person. So some people bring a little bag or something where you can put the things you care about, like your phone and your Apple Watch, just under the table. And as long as we know it's there under the table and you're not reaching for it, not looking at it, then that's fine as well. You don't have to be very far from your phone, as long as it's not like accessible to your hands. So at 7:30, so they'll give you warnings, like they'll say, okay, there's half an hour left, or there's 10 minutes left. When it's 7:30, they'll say, the test is now over, please put down your pencils. And so at that point, you really have to put down your pens, and you can get in trouble if you keep on writing beyond that time, so don't do that. So the term tests are run by TAs, grad students in this course, and they're pretty nice and friendly physicsy people. If you take a final exam in this course or any course at University of Toronto, they're run by what are called faculty invigilators. And most of those people are pretty nice too. But I mean I'll be there, okay? But I'm not in charge of the final exam. It's the invigilator who is above me in charge of the exam. And so I have done things like defended a student. Well, they only rated a couple more things to an invigilator, but they override me and they'll send you they're like cops. And you don't want to mess with the invigilators for sure. Not worth it. And then, so if you're still there right at 7:30, what you have to do, just as a warning, you can't just get up and leave. You have to wait till you're dismissed. Everyone has to sit there until every single paper in the whole room is picked up. And then once they're holding it in their hands and they're starting the count, then they'll say, okay, you're dismissed, and then everyone can stand up and start talking and leave. So please be patient at the very end. It says, please remain seated till you are told you can leave. Okay. I'd say maybe don't be late. I guess you could be late. Okay. The other thing that I would say, this is something that I certainly did, and I see a lot of students do this, and I think it's a good idea, is read the test before you start it. So spend the first 5-10 minutes even just reading through the whole test from front to back without answering a single question. That is actually, I think, good practice, just so that you know what you're up against. Even just skimming it, making sure you know how many questions there are, what's going on. Are there some conceptual questions that look pretty easy? You know, that kind of thing. I have found, too, that sometimes when I'm doing something else, the back of my mind's sort of working on something else. I don't know. If I know the whole test before I start in on it, really, I think it's good. Because you're also going to be dealing with time, right? Managing your time. And this is something I hear from so many professors in so many different courses, including chemistry, is that the most common mistake that students make on term tests and final exams is not reading the question carefully. And so you've misread the question, you answer something a little different. It happens a lot. So this is managing your time. There's it's 12. sorry. 11. Don't want to be confusing here. There are 10 multiple choice plus 1 written problems. So what is that? It's still around 7. You don't want to go way over and start running out of time. So try to keep track of that. But I mean, some of these are going to be conceptual, right? And those ones may only take a couple minutes. And I can't emphasize this one enough. You shouldn't have your phone on you. Don't get caught with your phone in your pocket, because then you end up going to the Office of Student Academic Integrity and all kinds of terrible things. No one wants to be there. The paper dictionary is an aid in case English is not your first language. Any translation dictionaries should be okay. So the invigilator might kind of look at it when they're collecting your signature, just to make sure you haven't hidden any extra physics material in there or something. But they might search your pencil case. I don't know. Probably not going to be too bad. When you're allowed an aid sheet, you would think that the invigilators would be a little calmer, but they're not. Okay. Guess what I'm going to do, actually, while we're here, got some time, right? Why don't I do an example of another Chapter 4 Pulley problem that I didn't get time to do before. And so let's go through this. I think this is an important one. Two blocks of masses M1 is 1 kilogram, and M2 is 2 kilograms, are hanging at the ends of a string that passes over a very light pulley with low friction bearings as shown. So, and it says, when the system is released from rest at time t equals 0, the bottom of M2 is 0.25 meters above the floor. So D here is equal to 0.25 meters, something like that. At what time does M2 hit the floor? Well, that's presumptive. Oh, it says, so I think M2 is greater than M1. And then it's a very light pulley, so what we've got is tension and tension acting up here. The same tension on both. But, so the tension's acting up on both. It's the same. And the gravity is acting down on both, and it's more on the more massive object. So I think, so therefore, just thinking about this intuitively, M2 will accelerate down. Does that make sense to you? It's heavier. It's a frictionless pulley, and at the same time, M1 will accelerate up. So they didn't really say it here, but I'm going to assume that M1 doesn't hit the pulley before M2 hits the floor, I guess. Assume M2 hits the floor. If I don't make this assumption, I can't solve the problem. Before M1 hits the pulley. I think even if it's a good thing to mention there. But what I'm going to do here is since there's two objects, I need two separate force diagrams. And there are a lot of ways of solving this, but what I am going to do is use different definitions of positive for the two things. So I'm going to find, by the way, the time for M2 to travel. D is equal to 0.25 meters. Okay. So, simplify diagram, I'm going to draw two force diagrams, one for M1 and one for M2. And they look like this. M1, so there's tension going up, and there's M1G going down. And for M2, well, I know you guys. I still think it's important to draw them to get. Sometimes force diagrams can look a little simple, and I think these are the force diagrams. Okay, so what's important here is the acceleration. Remember, and I tend to draw this off to the side, M1 is accelerating up, okay? And M2 is accelerating down with the same value of acceleration because they're both attached to that same string. If M1 goes up 1 meter, then M2 is going to go down 1 meter. And so they have to be traveling at the same velocity and the same acceleration. So what I'm going to do, and here's my trick, I hope you're okay with it, is I'm going to define for M1 plus equals up. And I'm going to define for M2 plus equals down. It sounds a little shady to do that, but I think it's okay as long as, because they're going to be two different equations, right? And represent mathematically. The M1 equation and the M2 equation. And if I do this, define plus is up for M1 and down is up for M2, then the acceleration A will be the same for both objects and the tension. And then we can just do two equations, two unknowns, and boom, boom, we're done. Okay? Want to do it? So remember, represent mathematically, it's always Newton's second law. F equals sum of forces is equal to M1 times A. And this one is the sum of forces is equal to M2 times A. Okay, so, and this is where it's going to be weird, because remember, for M1, positive is up, so tension is up, and then you minus M1G. That's the sum of the forces. And the sum of the forces here, gravity is pulling it in the positive direction, and the tension is pulling it in the negative direction. So this is, all the tricky stuff now has been done. This is the trickiest part of this question, is figuring out what you're supposed to do, and then setting up these equations somehow. And there's other ways of doing it, but I think this is the simplest thing. After this, it's just algebra, and I guess kinematics, but you can do these things. This becomes algebra, figuring what A is, and then it's going to be kinematics to try to, chapter 2, like try to figure out the time it takes. Got me? Should we do it? Okay. So the point here is that this is the same T and A for on both. And so what we're going to do is let's eliminate T and solve for A. So the way I like to do that is I just solve for T actually first and then set them to be equal. T equals M1A plus M1G. This one's a little harder. You have to add T to this side, but I think you're going to get that T here is equal to M2 times G minus M2 times A. You want to check me on that one? Does that look right? So step next is we're going to say T equals T. So m1a plus m1g equals m2g minus m2a. Now I'm going to collect like terms of a on one side of the equation and all the rest of the stuff on the other side of the equation because I'm solving for a. So m1a plus m2a is equal to m2g minus m1g. So that I can pull out a factor of a here. m1 plus m2 is equal to, pull out a factor of g there, I might as well. m2 minus m1, and now I can solve for a. A is equal to g times m2 minus m1 divided by m1 plus m2. Kind of makes sense, right? It's the driving force behind this is the difference of masses, I guess. If they were the same mass, you wouldn't have any acceleration. And then the kind of inertia of the system is both the masses together. So I like the look of this equation. And now I think we're ready to represent mathematically. We're still doing that, sorry. What are we doing? We're doing this now, which is that this falls some distance d is 0.25 meters. There's the floor. And so we've got the falling of m2. We know, let's keep track of what do we know? We know that v0 is 0, it's released from rest. We know d, and we know a, we just found a. We need t. What do we not care about? I guess probably we don't care about the final velocity. Just before it hits the floor. V final. Okay. So what I'm going to do is I'm going to use that d is equal to v0t plus 1/2 a t squared. That's the one where you don't care about the final velocity. And the initial was 0. So it's just simply solve for t. T is equal to the square root of 2 times d divided by a. So it looks a little nasty, but it's 2 times d. And divided by a, I'm going to do something like this. m1 plus m2, because I'm dividing. m2 minus m1. And now I can go to the next step, which is t, plug in the numbers. 2 times 0.25 divided by 9.8 times 2 plus 1 divided by 2 minus 1. So those are the masses. Plugging that all into my calculator, I got 0.39 seconds. Put a box around it, and you're done. So what I'm looking for, and also I might evaluate it, I guess. This is a small time, but it's only, going 0.25 meters. So it's reasonable. 25 centimeters. Okay, what time is it? Okay. Questions about that? We're good? Okay. So moving on, I would just say that some of the multiple choice questions, I think 3 or 4 of them, are just conceptual. And if you read through the test, you're going to see those. Sometimes the conceptual ones are the hardest ones, but they don't take a whole lot of writing, right? The other thing is that the last page of the test is a blank piece of paper. And so you can kind of gently tear that off and use that as scratch paper. And also, I'm going to be giving printer paper to all the invigilators so they have extra paper around in case you would like some extra blank paper. You can just raise your hand and they can hand that out. So it's good to have somewhere to do your sort of scratch work. If you start a longer problem and you're realizing it's taking you a lot longer than 7 minutes, you may want to kind of circle it and say, let's come back to this, and go on so you don't find yourself really running out of time and having to do like 5 questions in the last 10 minutes or something. Bring a snack or drink. So another thing that I would say is that this is something that helped me, and not everyone did this, is I got a good night's sleep before any term tests like this. And I think that's important on Monday night to sleep well. Because more important than studying the extra little things that you might be able to do in a couple hours in the night is having a well-rested brain. Oh my God, I'm starting to lose you guys. Let's do one more learning catalytics. It's survey. How do you feel? Maybe I'll ask you, how did you feel on Wednesday? A little curious about this. I think it's doable, guys. I think that you can do it. I do expect a lot of you, but I think you're up to it. It's going to be similar to homework questions, so let's see what people are saying. Okay. That's sort of more positive, I think, than negative. It's good. Good, you guys. I like that confidence. Like I say, we're going to continue. Whoop. Is that all? The plan is to continue along with Chapter 5. Something to think about, and this is something I promise I'll do on Wednesday, is swing a bucket of water over my head and see if I get drenched. So don't forget to be there. Good luck. See you Tuesday night.